So good afternoon, everyone. Welcome. If you'd like to take your seats, we will get started. So my name is Michael Thompson. I am the interim president of the University Corporation for Atmospheric Research, or UCAR. So welcome to UCAR's briefing on space weather and why it matters. First of all, special thanks to Senator Gary Peters and his staff for making this room available to us today. The format for today is that after some introductory remarks, we will hear from our three speakers. Then there'll be time at the end to answer your questions. So to start with, let me ask Senator Peters to say a few words. We're honored to have the Senator with us today. Senator Peters of Michigan is co-sponsoring a bipartisan space weather bill with his Senate colleagues Gardner and Booker. So we'd like to thank them and the Senate Commerce Committee for their support to improve solar storm forecasts and to protect our critical infrastructure and national security. So the Senator will make some opening remarks. Senator Peters.
Well, thank you, Michael. And it's wonderful to see such a great group here and a great turnout for this briefing on space weather, why it matters, and why we need to be thinking about it from a public policy perspective. I want to welcome each of the distinguished panelists that are here today to give a briefing on this issue. This is an issue that I've been working on for a few months now, and actually it came to my attention from the folks at the University of Michigan. Who are some of the leaders in heliophysics and doing some great work in the area, and talked about how we needed to learn a whole lot more about the sun and what happens on the sun because of the impact that it has with telecommunications and the electric power grid. And particularly when you think about what's happening in our country as we continue to get more and more dependent and interconnected with the internet and the Internet of Things that is coming out, in which literally everything that we have will be connected in some form or another to the Internet of Things. It's been described to me that the new systems on board will allow us to connect, if you want to put it in terms of numbers, I don't know what this number is, this is a big number, but it basically is equivalent to every grain of sand on the planet Earth can be connected through the Internet, is where we're going to be eventually getting to. And all that is powered by communications and powered by the electrical grid. And actually we are at a potentially very significant risk if we're not prepared for what could be a mass coronal ejection event from the sun. Not to mention the normal disturbances of space weather that occur on a regular basis that causes billions of dollars of interference every single year to GPS systems and other communication systems. But if we have a massive event, you're talking about potentially catastrophic event impacting the Earth. The last time we had a very big event was in 1859, the Carrington event, which you may be talking about. It happened in 1859. We didn't have a whole lot of electricity back then. The sky lit up. People woke up in the middle of the night thinking it was time for breakfast, started cooking breakfast because the sky was so bright as a result of this storm. The only thing that was really electrified at the time were the telegraphs. And my understanding is the telegraph system throughout the country basically was dysfunctional. And there were sparks and a shutdown of all of the telegraph. So that was the extent of the damage in 1859. You can imagine what would happen today with the amount of power that's out there in communications. In fact, Lloyd's of London did a study recently that said that if you had an 1859 type event in this country, you could see an impact up to $2.5 trillion negative impact to the economy. You can imagine that. Power would be out to up to 40 million people could be without electric power. And if the large transformers that handle this are destroyed, they could be without power for 12 to 24 months, a year or two. Can you imagine in this country 40 million people being without power, particularly some of the most sensitive areas, which is the eastern seaboard, parts of the Midwest where we're from in Michigan. But just imagine New York City without power for a year or two. What the consequences would be for our economy. This is something that we need to know a lot more about. We know we believe it's a 150-year event. I believe about just a few years ago, though, to give you a sense of how it's just a question of when this is going to happen. It's not if, it's when it's going to happen. In 2012, we had a storm of that magnitude miss the Earth by 7 days, I believe. By 7 days, we missed this type of event hitting us in 2012. And that's what we think is a 150-year event. We have really no idea what a 1,000-year event is. It could dwarf what we see as a 150-year event. So we need to be prepared. The legislation that I wrote with my colleagues, Senator Booker and Gardner, will allow us to coordinate this research, to put everybody on the same map, to make sure that we are thinking about this in a comprehensive way, understand that we need to be putting more resources into research. We have to learn just a whole lot more about the sun. I'm working with colleagues in the House. I don't think they've announced the bill yet, but we're looking at a bipartisan bill in the House as well that will likely come out very shortly. This is something that we hope that we move very quickly. It's common sense. And I think what you're going to learn today is it's something that we definitely need to focus on. The statistic that I'll leave it with, a statistic that I've heard, and our panelists might want to elaborate on it, but I've been told that the likelihood of a Carrington-type event, that 1859 event, over the next 10 years is about 12%. So we have a 12% chance of this happening over the next 10 years. To put that in terms that we could all appreciate, and I don't recommend anyone doing this, but if you think about playing Russian roulette, don't do this at home, by the way, but if you play Russian roulette, it's basically spinning the cartridge once and then pulling the trigger. That's the odds of this happening over the next decade. Do we want to take that risk? I don't think so. We need to learn a lot more. We've got to put the resources into the research, and then we have to make the kinds of preparations to protect our country and really the planet from what could be a potentially catastrophic event. But it all starts with science, it all starts with research, and that's what these panelists are going to talk about. So welcome to the event, and hope to get your support as we move this legislation forward. Thank you so much.
Thank you, Senator. That's a great introduction to the rest of this lunch program. Let me just say a few words before handing on to the first of our speakers. So for those of you unfamiliar with UCAR, UCAR is a non-profit consortium of more than 100 member universities that grant advanced degrees in the atmospheric sciences. UCAR also manages the National Center for Atmospheric Research, or NCAR, on behalf of the National Science Foundation. The research conducted by the UCAR community helps to inform decision makers. It also provides benefits back to society by improving our predictive and forecasting capabilities in the areas of weather, water, climate, and space weather. Several times a year, we bring members from our research community to the Hill to discuss the latest science in areas of importance to policymakers. So that brings us to the briefing topic for today, when we'll hear from 3 experts in the area of space weather, a key research focus for UCAR scientists. The driver of space weather is magnetic activity on the sun. Solar storms result when powerful magnetic disturbances on the sun eject charged plasma towards the Earth. As the nation's dependence on satellites and other high technology increases, so does our vulnerability to space weather. These extreme space weather events pose a potentially catastrophic threat to the national power grid, communication networks, GPS navigation, and global financial markets. Not only can they interrupt critical infrastructure, they can also disable it, risking our nation's security. So one of these solar storms typically takes about 2 or 3 days to arrive at the Earth, but an energetic one has a much faster travel time of around 12 hours. The other challenge is predicting the direction of the magnetic field inside this cloud. Currently, we only get that information as the storm passes a satellite located just upstream of the Earth. So for typical conditions, we only have about a 45-minute warning, or as little as 15 minutes for a fast-moving storm. UCAR scientists are working to improve solar storm predictions to enable decision makers to assess imminent risk and protect infrastructure. Our research includes enhancing observations of the sun's magnetic field, improving the modeling capability to interpret the observations, and feeding these new observations into next-generation models of interplanetary space and the Earth's upper atmosphere. The immediate goal is to predict the arrival time, speed, and magnetic direction of an oncoming storm sooner than the current 15 or 45 minutes. Ongoing investment is critical to enabling unprecedented observations of the solar corona, with the eventual goal of forecasting an eruption on the sun before it even occurs. So to introduce our speakers, our first speaker, Dr. Scott McIntosh, sitting closest to me, is an NCAR senior scientist and director of NCAR's High Altitude Observatory in Boulder, Colorado. Dr. McINTOSH is an expert in solar cycles and how magnetism, mass, and energy are transported from the sun's interior in ways that affect our planet. Sitting next to him, Dr. Thomas Zurbuchen is Professor of Space Science and Aerospace Engineering at the University of Michigan. Dr. Zurbuchen is a specialist in the robotic exploration of space. He leads a team that is responsible for 5 instruments currently in flight, and he is actively involved in the development of another instrument. Vice Admiral Konrad Lattenbacher is Chief Executive Officer of GeoOptics, Inc., which delivers environmental data and services to scientists and public and private users. Vice Admiral Lattenbacher is a former Undersecretary of Commerce and Administrator of NOAA in the Bush administration. He is an expert in military infrastructure, which must be protected from solar magnetic disturbances. So without further ado, I will hand on to Scott McINTOSH.
Thank you, Michael. Good afternoon, everyone. As Michael said, I'm Scott McINTOSH. I'm the director of the High Altitude Observatory and associate director of the National Center for Atmospheric Research in Boulder, Colorado. Last year, the High Altitude Observatory celebrated its 75th anniversary after being constituted to deal with the icky problem of radio disturbances at the onset of World War II. A bunch of colleagues were driven out from Harvard to the mountains in Colorado, to the pristine skies, to observe the sun and report back to Washington on any potential disturbances that would then impact radio communications with soldiers in the field. Our field, solar physics, had advanced a great deal in that 75 years. And of course, the little known fact that we live in the atmosphere of our star. The sun relentlessly bathes our planet with light and particles that form the basis for what's become called space weather. Much like the analog outside the room, there's no humidity in space. But much like that analog, space weather ranges in severity all the way from the benign, almost persistent, kind of flat calm of space, to stormy conditions, and all the way to cataclysmic storms, like Senator Peters introduced us to this concept of the Carrington event or the Black Swan event, the once in a century event that has the potential to destroy critical pieces of infrastructure and technology. Now, this beautiful animation that comes from NASA's visualization lab shows a stream of particles coming from the sun and bathing our planet. And if you watch closely, you'll notice that that stream of particles becomes greatly intensified as a coronal mass ejection takes off. Now, coronal mass ejection, or CME, is basically the most devastating, impactful object that can come from their sun. And you can kind of think of it as a space hurricane, if that makes it somewhat easier to understand. The problem, of course, is that there's a magnetic field in interplanetary space that makes things more complex. 75 years on, our mission to understand the relentless connection between our home and our star is reinforced by the technological dependence of society. Recently, in the last few years, the US space weather research community has worked in partnership with agencies and other federal organizations to develop a national strategy to improve forecast capability for space weather events. Now, many of you, especially if you've traveled further north, will know that the raw beauty of space weather in the form of the aurorae, but it actually can cascade down to ground level events such as disturbances of the power grid, space infrastructure vulnerabilities in communications and GPS, even down to your Visa card transactions. Because they're all time tagged by GPS, they're all vulnerable to even the most benign events of solar activity. Now, the current paradigm for space weather prediction is not like storm prediction, like the analog here is Hurricane Ike. We don't have instruments all over space that can help us map out the exact path of a solar hurricane as it leaves the sun and comes to Earth. We have a few hours immediately after it leaves the sun, and then, as Michael said, anywhere between 15 and 40 minutes upstream of the Earth. There's a 93 million mile gap in between. That doesn't sound very far, right? The sad analogy of this lives in the Galveston hurricane of 1900, where there were reports of hurricanes in the Gulf, or severe pressure disturbances in the Gulf, but no idea of impact before that event hit the town and decimated it, to the cost of about $100 billion in today's money and the loss of about 6,000 lives. But our forecasting capability right now for solar events is pretty much the same. We have an inkling of disturbance, and then we see it. We've got 20 minutes to react. It's not an ideal situation. So, what do we need? As Michael indicated, and I think as Senator Peters also indicated, we need new observational strategies, not only for the sun and the sun's magnetic field, but also for interplanetary space to sample the 93 million mile gap. But then, at the catcher's end, how is the Earth's magnetic field going to react to this storm? And then how is that storm going to cascade down into the lower parts of the upper atmosphere? Part of that, of course, requires next generation modeling capabilities, because models allow us to stitch observations together. Observations are discrete points in space, but the models allow us to put these things together and put them in an absolute context. And I would say that my personal pet project is that understanding all of that leads to understanding of black swan events. Once you can get ahead of that global picture, you can actually start to look at months, years, and maybe even decades in advance to understand the origins of truly cataclysmic solar events. Of course, one of the things that we're working on is a new observatory to observe the inner magnetic field of the sun. And of course, this animation here shows what a potential model or a next generation space model would look like that's fed by observations. This critical need to measure the magnetic field both on the inside, on the surface, and in the immediate exterior atmosphere of our star, the corona. And so we've developed this suite of instruments called COSMO, the Coronal Solar Magnetism Observatory, and it's capable of giving you that critical measurement of the directionality of the magnetic field as it leaves the sun and starts to propagate into interplanetary space. Now, at the other end of the system, in the Earth's upper atmosphere, is a truly dynamic place. It's the nexus of weather and space weather. There's weather radiating upward from beneath and solar perturbations raining down from above. And so it's actually a critical place where radio communications can be reflected, refracted, disturbed, destroyed, you name it. But the next generation of models are being developed in this critical environment, an environment where GPS satellites fly through. And that when coupled with the new observations from the US-Taiwan Cosmic Mission, the GOLD and ICON missions from NASA, will provide unprecedented ideas of how the ionosphere, the Earth's upper atmosphere, reacts to solar storms and those radiating above, like the one on the left, which is actually a typhoon radiating stuff into the ionosphere. But without, you need a synthesis of model and observation. And so that comes through a process called data assimilation. And this is a process that's been widely used in the meteorology community for a long time. But it's now only being implemented in the space weather domain because the observations are still pretty sparse. But it's a critical need that if you're going to have better forecast models, you need to be able to ingest the cutting edge observations and feed them through to improve the forecasts. And so to hand off to my next speaker, Thomas, space weather is a full-time concern. Both benign and extreme flavors of space weather can impact society and critical infrastructure at different levels, and often it can be rather sneaky. There could be a hefty price, and there probably is a hefty price to pay for negligence in forecasting episodes of extreme space weather. Improved observations and modeling capabilities work hand in hand and must work hand in hand to improve the forecast skill that we currently have up from maybe a few hours to maybe days in advance. And of course, we at NCAR are working with our partners in the university community and national agencies to develop key infrastructural pieces to understand those critical boundaries of the system. And thank you.
you're going to hear from 3 partners who really work together on space weather. And of course, I'm representing the academic community. I'm working at the University of Michigan. And like many other universities in many states, we're contributing to this problem. And somebody asked me recently, how did space weather change your research? And I think for me, the best analogy is the one that I put here. Space weather is to space researchers what cancer is to biological sciences. With the emergence of the recognition of the importance of space weather, we figured out a way to demonstrate the value and impact of one's work. The impact that really helps protect these important systems. If we lived in caves today, this would not be important. If we live in a technological society, this is of critical importance, and everything that has been said is absolutely important. So what do universities do? Well, we do a number of things, and first and foremost, of course, we do fundamental research of these physical processes that underlie space weather. We do so through investigations, data analysis, and building models. We also have a lot of the knowledge and understanding of instrument designs as compared to other communities. Many of the instruments in this community are actually built at universities, often together with companies. And we also have done a lot of applied research in building these large-scale models. I'm going to tell you kind of what we're doing at Michigan with this, the analysis and prediction of improved methodologies. So we actually learn how to do better in partnership with national labs and so forth. And then finally, and perhaps the most important thing, we educate the talent that powers the kind of space weather enterprise in the country, both at companies and in labs like Scott's. So we already heard this. I call this the Peters slide now. He gave you every single one of those numbers. I'm not going to repeat. The point is just really the kind of day-to-day damage right now of this is in the order tens of billions of dollars a year between the US and Europe alone, and can be up to trillions of dollars, depending on what that is. And really thinking of, I was just in New York City a couple days ago, right? Thinking of that city without power for extended periods of time, months, is unimaginable. I would not want to be there. Probably prefer being in the UP, the Upper Peninsula. Anyway, so what does the challenges that we have right now is really to take the forecast that we have from these minutes, tens of minutes, call it 48 minutes, up at L1, just kind of 1% the distance to the sun. One of my instruments or 2 of my instruments are sitting there and are measuring the solar wind as we speak, and basically looking at this. So we know what's happening there, but we'd like to propagate that and make it a 48-hour or so forecast, which includes everything that Scott just said, really understanding how the magnetic field is fed in. And so that really involves 3 challenges I'm going to quickly touch on: a modeling challenge, an observational challenge, and an education challenge. In each case, I want to focus on what's really new about it right now. This is a modeling challenge. The point here is not that I talk about each one of the boxes. The point is for you to understand that the challenge here is a multi-physics, multi-scale system that is deeply connected. On your left, you see solar type of phenomena of the type that Scott talked about within the solar surface, and on the outside, the corona. You see the kind of interactions that perturbations have in that atmosphere, and then how they propagate into space. And in fact, through that kind of shock that's forming at that interface, it's almost like a supersonic boom that you hear when an airplane goes over you. That kind of shock accelerates particles and kind of radiates space instruments up there. Once they hit the Earth, of course, a whole bunch of effects happen. Aurora, the most beautiful ones, but also a bunch of things that's highly concerning. Ground currents being one of them. So if you have a cable that's just sitting there, nothing attached, and one of these events happens, all of a sudden a current is flowing through that. So if you, for example, you're a power company and you power your system and currents are already flowing, all of a sudden Mother Nature adds a lot of current. What can happen is these transformers overheat. They burn through. That's what the senator was talking about. So that's really the nature of these ground currents. The other nature, of course, is the space assets, GPS. The only way I find my way around town is using the GPS. It's these assets that, of course, are vulnerable to radiation as well. So the University of Michigan built that model, as did others. You see a bunch of other models that are there. It's really important that more than one model is built, by the way, because they keep each other honest. They push each other. That's really important. Competition really matters in this. But the University of Michigan did really well in these various competitions that were done externally by NOAA. And actually, we're excited that now this model is run by NOAA supercomputers 24/7. And so the kind of model that we're thinking about, you see on the left there, is the data that are coming in at L1. Remember my spacecraft up there, and there's other instruments that get these data, and all of a sudden you see these predictions of ground currents in these colors. The more red, the more likely you have ground currents, and you see over Michigan or elsewhere, you see these ground current likelihood going up. It's these kind of predictions that these models now can do, and we're learning about the feasibility of the models. We're just at the beginning, like Scott said, but we're starting to make real progress. The other one that I want to talk about is new architectures in space. Scott talked about the fact that the space is largely empty and vast emptiness. We have no data there. What you really need to do is instrument space. And I was actually lucky to have chaired a National Academy report just recently focused on small spacecraft. We're just at the verge together, not just with academia, but also very much in partnership with companies of the type that you're going to talk about, to really bring these constellations of spacecraft up there. So for the first time, we have the visibility of the actual interactions in the Earth magnetosphere, or the actual interactions in the space between the sun and the Earth. So this is just happening right now, and these future architectures are just being invented, are just being thought about right now. This is an example from Earth weather that shows kind of the power of such architectures. And this one is focused on surface winds and hurricanes. Normally, the way you do this, you have a big radar. If you want to buy one, it costs you between $1 and $1.5 billion or so. And the radar shines light down, it comes back. And if the surface has no waves, it's like a mirror. It comes back really narrow, right back to you. If there's a lot of waves, it gets all messy, right? It gets incoherent. And so you can measure that return signal and deduce what's there. Well, what you can do for less than $200 million, which is what this one costs, you can build 8 spacecraft that actually don't look at radar, but look at GPS signals that are reflected off the surface. Not only can you do much of that research that you could do with the radar, but can you do it with a repeat time of the order 10 minutes, which is the relevant time, as opposed to many hours if you only have one asset in space. So that's the power of these big constellations that really are just at the verge, both here in Earth weather, but also in space weather. There's a lot that is happening on the progress, again, in private companies, in academia, in labs, and both on propulsion, attitude control, radiation tolerance. It's really important that these assets survive the storms that they're supposed to measure. And so a lot is happening. We're really excited about it. Final challenge is about this happy guy there with his spacecraft, is really about education. We think that the training of that talent, the kind of deep awareness of the importance of space weather in the context of space science is absolutely critical. And we want students that are in our universities to learn about both the sensors, about the models, and also the big data and the kind of impacts that space weather has. So with that, I'll turn it over to you, Admiral.
Good afternoon. I'm not quite as tall. Okay. All right. It's a pleasure to be here. I thank all of you for coming and spending your lunchtime where you could be doing something maybe, I don't know, a little bit more fun than listening about space weather, but still, I'm very pleased you're here. I was introduced to this in sort of a rude way earlier in this century when I took the NOAA job about a year into that, and they were looking at the budgets and that sort of thing. The first thing I had, well, Congress is going to cut that budget by a half. We don't need space weather stuff. So we fought to get that back, and we did. And the next year, it came in, we're just going to eliminate space weather. There will be no budget at all for space weather research. And of course, I hit the ceiling along with a lot of other people too. And the first answer came back, well, you don't need to do that. That's not NOAA's job. It should be the Air Force or NASA or somebody else. Somebody else does that. You don't do that. So of course, those are the only 3 agencies that do it, are NOAA, NASA, and the Air Force. And by the way, they work together, which is an exemplary action for our government to actually work together to have a joint center to do that. In any case, thanks to people I know that are in this audience, we were able to recover that cut and actually increase, modestly I'll say, the amount of resources that go to space weather. And hopefully those of you that are already in the audience, because you came today, and if you've just listened to our distinguished panel, you know that this is a really important issue for the nation. And it's not something, what I'm here to do today is talk about the fact that it's not just a government issue, it covers everything. And I like to think about it in the weather, terrestrial weather aspect, where you have a partnership between the research community, the government, and the commercial sector, because it's something that can't be solved by the government alone. It has to be a full, united effort by the entire population of the United States. These are going to be very serious events. So let me, so I'm going to talk to you a little bit about, quote, what the government's doing right now and how it's come along through 2 administrations to the point where I think we're in much better shape, and thanks to folks like Senator Peters and the Commerce committees and science committees that have helped us with this. I'm very grateful, and I encourage continued support of this program. But today, the administration created a national space weather strategy and an action plan. And you don't have to read the whole thing, but what I want to point out, and it's very, I won't say it's unique, but it's very forward-thinking in that it talks about a full national effort. It talks about a collaborative environment where we have government, industry, and people, because this is going to affect the entire population. And we don't know where it'll hit because we can't determine where a solar storm is going to hit. And it'll be international, too. It could go anywhere on the Earth. We can't target this like we can by a hurricane. We can sort of pinpoint where that goes these days. So this point about leveraging existing public and private network of expertise and capabilities is the takeaway from this slide. I want you to realize that that's very important for this, because this is a serious national event. And it's on the emergency situation list for the White House. This is something, if it happens, the Situation Room will be enacted. We'll bring all the folks in from the military and every agency, and it will become and it is now on the the exercise list, the top level exercise list for the country. So we've reached the point where I think the understanding of what the issues are much better. So let's move on with that. That strategy has 6 important goals, and I put this up there not so that I can read each one of them to you, but I want you to realize that it covers the entire gamut from planning benchmarks, from weather events to the operations, to the modeling, to the assessment, to the emergency management, to the forecasting services, and increasing international cooperation. Which, as I said, this will be an international event, too, because we don't know where the thing will hit, if it hits, when it hits. Actually, these things hit all the time. You might not realize that. They just don't put you in too much inconvenience, because people are getting forecasts and they're reducing power here and there, and they're watching our communication systems when we have some of the lower level events that come along. So let's talk about the full national picture. So there is an American Commercial Space Weather Association. It is filled with companies that do everything from the basic research and algorithm development all the way to helping emergency management. And the point of this is the government doesn't have enough capability internally to help everything all at once when there's an emergency. You have to have set this up so that there are commercial companies that help other commercial companies, power companies, the communication companies, the satellite companies, the airlines, medical facilities, all the pieces that are needed, that it can't be done just by actually just passing a bill and providing a little bit of money. It's going to take a national effort. So if you look and go through this, you can see that just about everything that you can think of has some counterpart commercially. And the important point is to make the commercial a part of the way we react to these events. And this is where we are. This is my heuristic model. We have, the way I see it, a very small federal government budget. The budget for the federal government is very small. So the federal government can't do everything for everybody. When we do that, we don't, we miss the boat. We have a lot of needs, national needs, huge national needs. And particularly in space weather, we have to figure out how to fill them like instantaneously. This is not something you can wait over 15, 20 years to do. It's got to be ready right then. And how can we do that? We do that by having this cooperative environment between research, academia, the private sector, and the government sector working together, looking at the places where there are swim lanes I like to talk about in terms of places where something is very much suited for value-added commercial services, as well as the basic warnings and forecasts that come from the government and the setting of emergency conditions and the rule sets that allow us for every party to play his role, his or her role in this. And with that, we can do it. It needs a full court press. I want to point out we're aided in that, aided and abetted by the government space policy, which, by the way, has also been consistent across both parties for the last 20 years, at least. And that is that space systems should be used, commercial space systems should be used when it exists. The U.S. government should go to commercial services. That's the point I'm trying to make. And these are just a few of the lines from the current administration space policy, which is similar to the space policy from Bush, as well as Clinton, et cetera. Go back as far as you want, you'll find the same language. So there's incentive for us to create a commercial space sector, and this is part of it. And to look at, I'm showing you the logo for the industry association, which exists to bring all these folks together. They hit all levels from upstream, midstream, downstream. Everywhere you want to go, there are some experts that can help. And when you need a full court press, and actually day to day, power companies need this kind of information continuously. It needs to be tailored for their use and their kinds of installations and where they are, along with all the other airlines, everything else. So it's not something the government should do from a tax basis. It should be done for, it should be accommodated in the normal press of business in the United States. That would be the best way to do it. So I want one slide, and I'm going to quit. This is, as I'm the military rep here, I have spent, 47 years out of my last 55 on the planet as a public servant, and 40 of those years were in the United States Navy. So I have been trained in nuclear exercises. I have exercised for nuclear warfare and for all of the issues that you have with that kind of a disaster and catastrophe. And so, as I mentioned, this is an event like this is it's not only national, it's international. It's going to affect everything we do. It affects the military. The military is affected just like everybody else. And one of the biggest issues, the electromagnetic pulse, or high altitude HEMP, as we call it. This is from the solar storms. They can have the same effects as a nuclear bomb has. They can cut out all your communication. They can actually provide some radiation. They do the things kind of caused by a solar flare. We have a whole different level set of storm codes like we do for hurricanes and tornadoes, et cetera. And E3 storm is a category of storm. And so it's an extremely important military event as well. And the military will be part of the response. And the military folks are trained in this, but it's not something they want to do, I can assure you of that. So the last note there is that the House and the Senate are interested, and I really appreciate that. And we're here today to help explain the seriousness of this situation that we have with space weather and the need to support a full effort with using all elements of our society to protect and defend against this. With that, I will stand adjourned. Thank you very much.
So thank you very much to all three of you for that fascinating briefing. And now it's your turn. The speakers will be very happy to take questions.
So, as you know, we're having this discussion kind of on the weather side too. How do you
see, is this on? Can you hear me? You can hear me. I guess you can't. I would commend, and you probably have looked at it, but many in the audience haven't looked at it. There's something called the Fair Weather Report that was put out by the National Academies in early part of the century, early part of my tenure at NOAA, and it's a very good analysis of the situation, what private can provide, what government provides, what academia provides, and it talks about how to work together. And basically what it says is you have to plan together. So you have to talk to each other. You have to have groups, and that's why I've mentioned the AXWA Association. So we have associations in the space weather side where we can talk with Congress, we can talk with the administration, we can talk with the government agencies, and we can plan together. So planning is important because every time some new gimmick comes on the stage, everybody says, well, that's mine, I'll do that. Well, not so fast. Wait a second. If that requires a big tax load on people for a return that goes to an individual private company, let's think about that one a little bit. Is that something that ought to be provided by the private sector and not by the government? Just simple example. But the idea is that you don't do things helter-skelter. You work together. And you plan together so that you're not stepping on each other's toes, that you're actually complementing each other. The whole thing should not be a total competition. The commercial sector is going to compete with each other, but they shouldn't be competing with the federal government or with academia and the research community that provides the basis for it. That ought to be put together in a unified way. And I think the Fair Weather Report, and there's been a couple of other papers that modify that. That's been working pretty well. And so I think the same kind of thing ought to be applied in this area.
Thank you.
So thank you guys all so much for coming. I had a quick question in regards to the EMP threat that can come from a nuclear storm. I was wondering if you can just elaborate more on what are things that we can do to prevent that from happening, and on the flip side, in case something like this does happen and we're not prepared, and we do have a 10, 12, 24-month period where we don't have access to electricity or some of these functions, how do we respond to a disaster like that?
That's a great question, and that's why we're all up here, because I don't believe we do have adequate response in all situations. There could be some very serious situations where we are not capable of responding. At least at this point, we know we have a problem. We've started to set up the right kinds of things to do, and we're working together. And the question is, we have to up the pace so this 12% doesn't come along, in the first of the 100 points that you're talking about. But first of all, in the last 10 years, there's been a great deal of increase in understanding. So the people that are affected, we've talked to the airlines. They understand. They look at radiation measures for their pilots, radiation badges, and that sort of thing, so that they don't get caught. We look at the power companies. They know, and they regularly exercise lowering the power based on the reports they're getting today. So there's been a gradual improvement in our ability. But if you have a Carrington event or something that goes way beyond, today we can handle sort of like what I would call low-level average kinds of things. There's enough out there. But when you get to a large-scale event, you're going to have a problem. I'll open this up to my other folks. They want to jump on that. I wish I had a good answer. That's why I'm here screaming about this, because it's very important. And I've been doing that for 14 years.
So one thing for sure is that we can't prevent one of these Carrington-like events from happening at some point, as the senator said in his opening remarks. And as he also mentioned, back in 2012, we observed one of these ejections from the sun going off at 90 degrees to us, which is where he was saying we missed it by 7 days, because if the sun had been 7 days earlier in its rotation when this had gone off, then it would have come straight at us. So this is why it's really so critical that we improve on this 15 to 40-minute time that we have at the moment, which tells us what the conditions in this approaching storm are and whether they're going to be relatively benign or whether they're going to be catastrophic.
Yeah, and to echo what Thomas talked about in terms of the instrumentation of space, if you want to get even further ahead of the game. You need to be observing from the 90-degree angle. So you need to observe sunspots and magnetic activity as it rotates towards the Earth to watch it as a kind of first thing, because the models that then take those observations don't really critically exist yet. And so we're pretty much only looking at our one local look at the sun, one time. So we don't really see what's coming around the corner. We have hints at it, but we don't see it. And so instrumenting space is a critical step to get to that next level of forecast capability, because, as Michael said, you can't stop them, but you've got to prepare for them.
Think of it as what we did with the Weather Service after the year where we had Katrina and a strong hurricane season. You all gave us enough money to put hurricane warning buoys further out into the Atlantic. So the Weather Service has warning to give us, extra time, another 24 to 48, 72 hours. We need the same kind of things out in space. Okay, we need satellites at different positions that can give us a time stream of things that are coming. That would help a lot. And of course, the other piece is having reserve transformers for the electrical side of this would really help. And I think power companies are working on that, but it could be better.
James.
So when you talk about instrumenting space, are you talking about extremely high Earth orbiting instruments, or things that are orbiting the sun that with us, or
Orbiting the sun.
So it's really both, right?
It's both. But you've got to cover that whole distance. Go ahead.
Right. The hard part is to instrument space around the sun. So kind of, we're going around every year, right? So what you'd really like is kind of go at other longitudes, so to say. Kind of, so if something goes 90 degrees ahead of us or 90 degrees behind us. So we really kind of see the evolution of the magnetic field. One of the things we learned about the sun in the last couple decades is how non-local things are. So in other words, something affecting and a kind of an emergent magnetic structure kind of away from us can actually create a perturbation in our direction in a way that we would have never predicted if we didn't see that. So it's really about instrumenting that.
Jamie Hawkins, Lockheed Martin. Regarding the comprehensive observation system, would you care to comment, Dr. McIntosh, on international roles? This is a worldwide problem, not a United States problem.
Correct.
If you meet with international partners, you would have waterfront coverage.
That's true. And I think there's a lot of interest both at the European Space Agency level. These are at national agency levels, and the Japanese at JAXA. And I think space weather truly is an international problem. And I think when you're talking about the levels of funding required to instrument space, as Thomas and the Admiral have talked about, you need international collaborations, because it's probably more than one country can afford on its own. But it's a critical need.
I just want to point out, so even 10 years ago, we would have guessed that it's important to instrument space to kind of really have these other viewpoints. The one thing that happened in the last 10 years is that we actually developed technologies that make that affordable. Like the technologies, like if every single one of those sentinels, so to say, is $1 billion, it's easy to add up, right? How many billions it takes to kind of get enough resolution. That's no longer the case. I mean, kind of the point of that intermediate part of my presentation was, hey, there's tremendous technologies, in part, of course, developed at your company, but also at academia and some of the government places, is really to have technologies that this can be done at a fraction of the cost, so it becomes affordable. It's not only necessary, but it's also affordable within the budget.
One here and then one at the back.
I'm Frank Loring with Aviation for anybody. The idea of instrumenting a larger area of space seems to lend itself to maybe hosted payloads on commercial spacecraft. I wonder if any of you could describe that, and for you, Admiral, how that might play into some kind of commercial role. In other words, who would the customer be, and what would the service be that would be provided in broadening the instrumentation for the study?
I think when you come down to putting things out economically and covering a large area, a commercial service is a good alternative. I love the federal government, but the federal U.S. government is not the most efficient provider of services, and even our ships are still built. Navy ships are still built commercially. Anyway, where you have commercial services that provide activities that are important for the federal government, you need to have some support for that. In other words, you need to allow for it in the terms of whatever legislation there is, so that there's some competition for doing this. If you have one provider and it's the federal government, you end up spending a lot more than you do if you have a commercial set of companies competing and doing it. And it's just, I mean, that's just the way it works.
Yeah, and I do believe that the tremendous changes that happen right now in the launch industry is really helping driving this cost down. You know, for a long time, it's really the launch cost that, in some of these cases, just made it not affordable. So it's kind of, if the launcher is $100 million or more, right? Kind of, it makes no sense to build a spacecraft that's cheaper onto it. So I think what you're going to see in many of these cases is spacecraft that are stacked on top of each other, are really launched as constellations, are using advanced propulsion to get into the right orbits. And you also will see, I think, in some cases, what we're already seeing now, secondary launch options, some of them canister, kind of in canisters, so it's easier to kind of integrate them, especially as test launches, but, such as CubeSats or others, but also other kind of secondary opportunities. So that sector, I think, has really made a lot of progress.
So it's more a CubeSat constellation, small sat constellation than hosted payloads all over the place.
So I think it's probably that. So the way I would see what's interesting about the Cygnus one is, at the end, Cygnus is not a CubeSat, but you cannot imagine a Cygnus without the CubeSat industry. So basically, what happened is, with that emergence of that largely commercially driven, kind of development, basically what happens is a whole set of parts and subsystems are available that you can use now to build a system, which you weren't able to do 10 years ago, even 5 years ago. I mean, a lot of this market has really just emerged. And so I think what will happen, if I had to guess, so I've built some of these systems, right? So if I had to guess, it's just kind of that some of them the vast majority of them, especially the ones that we're talking about around orbiting the sun, will not be CubeSats. They will be bigger. They're small satellites, but they will depend on technologies that are developed in the context of CubeSats, and a lot of the kind of scalability of how you launch them, how you integrate them, how you host them. I think all this stuff will be figured out in the next few years, and between the partners that are involved. I think that there's an interested community to really get involved. There's tremendous opportunity now that 10 years ago just wasn't there.
Yes.
You had mentioned a cost of $10 billion a year to the U.S. year. Can you provide a little more detail on that, or a reference?
Yes, I'd be very happy. I'll give you my card, and I'll send you the full reference. Every single number on that slide is quoted out of a detailed study. So the $10 billion is actually a study done by Swiss Re, kind of the reinsurance business that is really looking at industry impacts and specific analyses in a variety of sectors, and really costing those out, just the way a insurance or reinsurance company would do. So the number is a direct quote out of that analysis, which is in the public domain. I'm very happy to send it to you to look at. So are the $1 trillion. That's actually the $2 trillion is not only in the analysis that the senator talked about, which is really important, but also a National Academy analysis with a detailed economic analysis of the impacts that basically validated that number. The third number, the 12% in 10 years, is also a published record. So I'll send you every one of those numbers. None of them is made up.
So Thomas, that $10 billion a year, that comes from having to adjust the operations of the power provider?
Yeah, so basically what happens, right, because of the fact that when a warning comes, let's say I'm a power company, and so basically a warning comes, what you want to do because of the fact that currents are being driven in your systems, you want to ramp down your power. So basically, you want to create headroom. So if Mother Nature drives some currents, it's not driving you into the red. The moment you drop your current, of course, you sell less than you were going to. So there's less. There's a financial impact of that. The same is true with some of the space assets. And Admiral knows a lot more about details that I don't. In which you basically, when one of these perturbations happens, you are not able to really utilize it. In some cases, some of these space assets come down. Some of these, television satellites, every once in a while, they get knocked around by one of those, and you threat those events as well. So there's economic value that's being lost as a result of that. There's a variety of, specific mechanisms for that, but the result is the $10 billion or so.
Is it fair to say then that the power providers have to be overly conservative because we don't have good enough forecasts?
The forecast accuracy will make a huge impact on this. I talked to a number of, in my local power company, DT Energy, I talked to the guy who has to make that decision. And he tells me it's like how much he struggles with this, because every single time we do a false positive is when he loses money and he gets beat up. You ramp down the current and nothing happened. What are you doing, right? And so eventually he's just going to, get to bed and put the blanket over the head and hope nothing happens, right? And kind of a strategy based on hope, because you get beat up because of false positives. So the accuracy of forecast really helps industry make the right decisions, and also not negatively impact revenues in cases where it's not necessary. We just really don't, we're just at the beginning. We just don't know enough about it, unfortunately, to help that particular engineer or many others around the nation.
Question right at the back.
Well, it's kind of interesting that over the last few years we've observed that the sun actually is a little bit more hyperactive than its decadal scale variability, in that it has an almost annual scale of like a stormy season, if you like. And so we're starting to try and understand that, because it creates flares and CMEs and activity on that scale that actually doubles the number of events per unit time. And so that opens a whole new door to forecast capability. If you can tell at what phase of a given time period you are relative to the activity bursts on the sun, they come in clusters. And so there's a lot of research in that area. I think the modeling capability is advancing very rapidly to accommodate the observational advances that are coming too. So I think everything has to work hand in hand. There's a lot of things we don't know, but I think if we can consolidate effort and work together, we can push that envelope out to give power grid people that have got their finger on the current that kind of window of an all clear period. It's actually probably better to have all clear periods than know when, and how long those all clear periods are. So,
I just want to say it's a lot easier to get the TV interview after the TV satellite got knocked out, right? And than when it's not. So kind of in that sense, it's like hurricane researchers, right? It's a lot easier to basically explain the importance of some research kind of in the context of what's brewing out at sea, right? So in that sense, certainly activity kind of increases of the type that Scott's talking about help the communication. We do, however, because of that kind of 10 billion a year type of impact, it just really isn't the case that we're only looking at the top events, right? The impacts are always there, right? And kind of are really affecting us and affecting a number of systems. And so in that sense, the people who are building these systems or are impacted by them, for them, they need to wait for a major storm to be interested, right? It is there, ever present. So it really has both characters to it.
Yeah, my experience shows that we would be much better off if the sun would just get on the 4-year presidential schedule. We'd do a lot better in influencing people to support the space weather effort.
I think there was a question. Yeah, just there.
Comment on any relationship between the Van Allen belts and the Earth's magnetic field for space weather and space wind? And then sort of a related question, what considerations are there for long-term manned space flight, whether it's on the space station or colonization of Mars, et cetera?
So the Van Allen belts, as you mentioned, is kind of one of these big surprises. As you go up, radiation increases, right? Kind of, and many people thought it's the other way around because the Earth is, radioactive. So you put the Geiger counter to the ground, you see these counts. So the Van Allen belts, of course, are highly variable. Kind of, we're exploring them right now with the storm probes that are up there. We're learning about how these belts are increasing in magnitude, radiation, and are decreasing. So these belts you have to cross as you go out into space. So kind of like you mentioned, like if I'm hitching a ride well past low Earth orbit, for example, to cislunar space or eventually to Mars, it's the radiation near Earth that I have to get through, and then also the radiation in space. Now, it turns out there's 2 types of radiation in space that matters beyond the Earth magnetosphere. The first one is, I will almost call it like ever drizzle, like it's let's say it's the galactic radiation, between us, if I'm standing outside, between us and space, each square centimeter is a kilogram of mass that shields us, right? And the galactic cosmic rays, which is that drizzle, is actually in the long run the more severe radiation for astronauts, cancer inducing and so forth. That's the one part that Martian did not get right? And kind of that's a real issue and needs to be considered. The other one are the storms, just the same way as Scott is talking about, the storms near the Earth. Of course, these storms are also affecting systems on Mars. So the Van Allen belts are absolutely critical for assets in near Earth space, and also as we go through it, because they're the dominant source of radiation. Again, we're learning a lot about it, but it's these 2 other sources of radiation that I think for interplanetary travel and also kind of cislunar planet are absolutely critical. And the counterintuitive part is the galactic radiation is the dominant one. It's kind of that drizzle actually like gets us more wet than the thunderstorm from time to time. By the way, the galactic radiation has never been more intense than it is right now during the entire space since we were taking measurements of it. And kind of it's a thing we don't understand. There's certain things that the sun, Scott is doing research on, and others, like the solar magnetic field right now is actually lower than it has been for a while, which is actually not, it's not keeping out the galactic radiation more. So kind of right now, if you looked at the radiation an astronaut would get getting to Mars, it would be significantly higher than if that astronaut left 20 years ago, let's say, just because there's more galactic radiation. So both of these matter.
Right there.
Well, to answer the last part of your question first, I think there are plans in the works to replace the chronographic capability at L1. I used to work on SOHO, and from what I gather from talking to the project scientists is that the actual downturn in solar magnetism over the last cycle, certainly, maybe longer, has actually preserved the solar panels on the spacecraft. So if the sun had been as strong as it was a decade ago, SOHO would already be gone. And so radiation affects the efficiency of the solar panels. So actually, the fact that the sun's a little bit weaker has actually let SOHO limp along for a little bit longer. But I think, as far as I know, SOHO is consumables that could last a long time. So it could keep orbit. The problem is that the solar panels are decaying at such a rate, it can no longer power the spacecraft. So.
But your statement is absolutely correct. The space instrument is beyond its lifetime. I've built some things that are beyond the lifetime. Everyone's in a while, one morning you come to work and it doesn't work anymore. That happened to me with one of my instruments just a couple of years ago. We don't know what happened, right? It's electronics eventually, and that could happen to LASCO. We hope it doesn't because we do not have a replacement ready. It is, however, part of NOAA's plan to actually launch a coronagraph. I think it's a critical tool now in forecasting, really seeing these coronal mass ejections coming our way. It's one of the key ingredients, we think, in a future forecasting system. So yes, it's far beyond its lifetime. It's a miracle it still works, frankly, speaking as an engineer.
It's an incredible bus.
So time for one last quick question, if there is one. Michael.
Yeah, I have a question about just the investments that are made in basic research and education. And certainly the National Science Foundation is another big player in this space and funding research for space weather. I was curious, can you speak briefly to some of the innovations that have come from the academic community that have helped advance what's going on with space weather, data simulation, space observation, other aspects?
Needless to say, I believe in many ways the National Science Foundation actually was the first space weather supporting kind of agency, really building a space weather program that is really was pioneering in many ways. The model that I showed, much of the investments that created that model came out of the National Science Foundation through a series of investments, kind of sometimes focused on individual boxes there, really figuring out what the science is and then pulling it together into a forecasting tool. So it's that path, just the way sometimes the theory we have about kind of fundamental research, having impact really does work. And this is one of those examples. The one thing that's also worth talking about is that actually these kind of small spacecraft that we're talking about instrumenting space, that the first research program that actually focused on these small spacecraft, focused on science, came out of the National Science Foundation. I remember I was at that first workshop. My arm was a little bit twisted to go there, and kind of because having built instruments that are a lot bigger than the spacecraft there, I actually had some doubts of the value initially. Needless to say, me and many people who were a lot more critical than me, and various agencies are quiet now, right? Because there's a tremendous value that has already been proven, and I think the National Science Foundation just there really deserves tremendous credit of pioneering that, really creating a new capability, a national capability that is affecting not just the research community, but has already generated a number of companies, kind of the economic activity in just CubeSats. We think last year alone was of the order $1.5 billion. That is a new field that is just starting out, and so I think it's just a tremendous impact of the National Science Foundation in a number of cases. Education, of course, is the one that's always the hardest to talk about because we think about Anne and we think about Gina and we think about Ben and so forth who got education from the National Science Foundations and are leaders in both companies and in the federal government. So in many ways, that talent that we get out may have the most impact, more than any technology or model.
Yeah, and I would say also that given organizations like ours at the National Center for Atmospheric Research, where space weather people live with climate scientists, all those observational and data assimilation strategies that are being implemented in meteorology can and will be and are being investigated in how they are transported into the space weather framework so that when we have these new observations that we require, that they can be made operational as quickly as possible and also inform and feed back on the research and the models. So it's a real, NSF is creating a real vibrant atmosphere to explore this part of space.
So on that note, we will draw to a close. Please join me in thanking the panel members.